Hello there, and welcome to the Sleepy Space Channel. No telescope will ever photograph the first 3 minutes of the universe, because the cosmos was then a glowing fog through which no light could pass. And yet we know, in remarkable detail, what those minutes held. Tonight, we reconstruct them, second by second, beginning in a heat so great that the forces of nature were a single thing, and the universe was far too hot for matter to hold together. We will watch the universe stretch, the first particles take shape, and the balance of matter tip, until at last, at the age of 180 seconds, the first nuclei are forged. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is anything you need to carry. There is nothing here to solve, and nothing you must remember. Settle in. Let your shoulders soften. Let your breathing slow. Let the weight of the day fade gently away. Let's begin. There is a moment at the beginning of everything that no telescope will ever photograph. It is the first interval of the universe, the opening stretch of time in which the cosmos went from an almost unimaginable heat to the first quiet pieces of ordinary matter. The whole of it lasted only about 180 seconds. In that brief span, shorter than the time it takes to read a few slow pages, the universe settled the basic recipe of everything it would ever build. Tonight we travel back to that beginning, and we move through it slowly, in the order it happened. The story is sometimes called the first 3 minutes, and the name is close enough to be useful. A handful of the most important events take place even faster, in fractions of a single second. A little of the work trails on toward the 20-minute mark. But the decisive part, the part where the first true building blocks of matter were forged, falls within those first 3 minutes. It is a strange thing to consider, and at first it can feel almost unsettling. The universe is well over 13 billion years old, and yet the events that fixed the composition of ordinary matter were essentially complete before the 4th minute. Nearly all of the hydrogen and helium that exists today, the raw material of every star and every world, was either already present or had just been made by the time the universe was 3 minutes old. Everything since has been a long, slow rearrangement of what was settled in that opening. We begin where careful science itself begins, which is not quite at the very first instant. The natural place to start would be the absolute beginning, the moment often written as time zero. Yet this is exactly the place where the clearest thinking grows quiet. When the equations are run backward toward that first instant, they predict a state of infinite temperature and infinite density, and an infinity, in a physical theory, is usually a sign that the theory has reached the edge of what it can say. So the honest starting point is not the first moment, but the earliest moment that can be described with confidence. Below a certain almost inconceivably small fraction of a second, the two great frameworks of physics give answers that disagree, and no fully tested theory yet joins them together. That threshold is a kind of wall. Before it lies a question that remains genuinely open. After it lies a story that can be told with remarkable precision. It helps to clear away one common picture before we go any further. The beginning was not an explosion that happened at a single point inside an already existing space, throwing matter outward into a surrounding emptiness. There was no surrounding emptiness, and there was no single point. What happened was the rapid expansion of space itself, unfolding everywhere at once. Every place in the universe was part of it, because at the beginning, every place was pressed together into the same dense state. This means there is no center to the universe, and there never was. There is no location you could travel to and say that the beginning happened here rather than there. It happened in the spot where you are sitting tonight, and it happened with equal claim at the farthest place any instrument has ever seen. The expansion was not motion through space. It was the stretching of space, carrying everything along with it. We should also be honest about what this story does not tell. It does not say what came before, or whether the word before even has meaning when time itself is part of what is unfolding. It does not reach behind the wall of that first tiny fraction of a second. What it describes, and describes extraordinarily well, is the aftermath. A universe that began hotter and denser than anything that exists now, and has been cooling and expanding ever since. That single idea, cooling, is the quiet engine of everything that follows. The universe does not change in these first minutes, because anything pushes it or strikes it. It changes because it cools, steadily and without pause, as space stretches. Every event we are about to witness happens because the temperature crosses some threshold. A point at which something that was once impossible becomes possible, or something that could never hold together is finally allowed to endure. So hold that in mind as we set out. The universe begins almost unimaginably hot, and it cools without stopping. As it cools, it passes through one threshold after another, and at each threshold, something new becomes possible. The forces of nature separate. The first particles of matter take shape. A near-perfect cancellation leaves behind the thin residue that becomes everything. And, at last, around the 3-minute mark, the first nuclei are forged. We start at the edge of time, where the fog first begins to thin. Consider, for a moment, how short 3 minutes truly is against the age of the universe. If the whole history of the cosmos were compressed into a single year, the first 3 minutes would not even register as the smallest fraction of the first second of that year. They are a sliver at the very start, briefer than any comparison can comfortably hold. And yet that sliver did more lasting work than almost all the long ages that followed it. There is also a reason the first minutes can never be seen directly, and it is worth understanding from the outset. The early universe was filled with light, so densely that it was opaque, a glowing fog through which no clear image could ever pass. No telescope, however powerful, can look back to those first minutes and photograph them, because there was no clear light to carry the picture. What we know of them is reconstructed, pieced together from the traces they left behind. So when we ask what the first 3 minutes looked like, we are asking a careful question. There was no eye to see them, and no clear light by which to see. But the physics that governed them is well understood, and the fossils they left can still be read. The picture we build is not a photograph. It is a reconstruction, drawn from evidence and from the steady laws of nature, and it is detailed enough to walk through slowly. The temperatures of those first minutes are beyond anything in ordinary experience, and it is better to feel their scale than to count their digits. The universe began far hotter than the core of any star, hotter than the center of any explosion, hotter than any furnace that could ever be built. And it cooled with each passing moment, from that almost limitless heat toward the merely enormous, and then toward the warm, and at last toward the cold and quiet cosmos of the present. What we will witness then is a universe cooling through a sequence of moments, each one making something new possible. We move through it as patient observers, watching the thresholds pass, watching the first matter take shape. There is no urgency in it for us, only the slow unfolding of a beginning that finished its most important work long ago, and has been at rest with that work ever since. There is no need to hold any of the numbers or the names that follow, for they are only the scaffolding of the story. What matters is the shape of it, A universe beginning in a simple and almost limitless heat, and cooling through one quiet threshold after another into the foundation of everything. The details can wash over you like the sound of moving water. The shape is what remains, and the shape is gentle. We will move slowly, in the order things happened, and we will not hurry past anything. Each stage will have its moment, and each will settle softly into the next, the way 1 hour of the night settles into another. There is nowhere we need to arrive, and nothing we need to finish. There is only the slow unfolding of a beginning that has already happened, long ago and completely, with nothing left for us to do but watch it. For now, simply settle into the scale of it. We are going back more than 13 billion years to a universe with no stars, no galaxies, no atoms, and no darkness anywhere, because the whole of space was filled with light. There was nowhere to stand and watch it from, because all of space was contained within it. This is the universe in its first moments, and we will move through it gently, one threshold at a time. In the earliest moment we can describe, the universe was so hot that the forces of nature were not yet the separate things we know today. This is one of the most quietly remarkable facts about the beginning, and it is worth lingering on. The nature we live inside is governed by 4 basic forces, and in the first sliver of a second, those 4 were not yet distinct from one another. Consider what those forces are in the present universe. Gravity is the gentlest of them, and the one we feel most directly, the force that shapes the orbits of worlds and gathers matter into stars and galaxies. Electromagnetism binds electrons to atoms and carries every ray of light. 2 further forces act only across the tiny distances inside an atomic nucleus. One is called the strong force, which holds the nucleus together, and the other is called the weak force, which governs certain slow transformations of particles. These 4 forces feel entirely different from one another in daily experience, and they operate on wildly different scales. Yet physics has long understood that at very high energies, several of them begin to behave as facets of a single underlying force. The differences between them soften and then disappear as the temperature climbs. And the early universe was hotter than any energy we could ever recreate, hot enough to erase those distinctions entirely. So in the first instant, the forces were unified, or very nearly so. There was a simplicity to the universe then that it would never have again. As the cosmos expanded and cooled, that simplicity began to break apart. The forces separated from one another, one after another, in a sequence often described as a series of thresholds, each crossed as the temperature fell past some critical point. Gravity is thought to have become distinct first, parting from the others at the very earliest moment, near the edge of what can be described. Then, a little later, and a little cooler, the strong force separated from the rest. Each of these partings was a kind of change of state, not a change of ingredients. Nothing was added, and nothing was taken away. The universe simply cooled past a point where what had been one thing settled into 2. There is a familiar comparison that makes this easier to hold. Water releases energy as it freezes into ice, and the ice that forms is not a new substance, but the same water settled into a new arrangement. The separation of the forces was something like that. As the universe cooled past each threshold, it settled into a new and more structured form, releasing energy as it did so, and what had been unified became distinct. It is important to be honest that these earliest transitions are among the least certain parts of the whole story. They happened at energies far beyond anything that can be produced or directly observed, and so the picture of them is built from theory rather than from measurement. The broad sequence is widely accepted and well motivated. The precise details remain a frontier, a place where understanding is still being worked out. This is not a weakness in the account, so much as an honest edge of it. The universe at this stage is being described at energies no laboratory will ever reach, and a certain humility is the correct response. What can be said with confidence is the shape of the thing, a universe that began with its forces joined and unfolded them one by one as it cooled, growing more varied and more structured with every passing fraction of a second. For the listener, the technical names of the forces are not what matters. What matters is the feeling of a universe simplifying as it is run backward in the mind. Picture the present cosmos, with its 4 distinct forces shaping everything from the fall of rain to the binding of atoms. Now imagine cooling that picture in reverse, watching the forces fold together, 4 becoming 3, 3 becoming fewer, until in the first instant they may have been a single thing. There is a strange comfort in that image. The universe we know is full of variety, full of different forces pulling in different ways. But underneath all of it, at the beginning, there seems to have been a unity, a single simple state from which all the variety later unfolded. The richness of the present is not how things started. It is what cooling made of a simpler beginning. As the forces finished separating, the stage was set for the next chapter. The universe was now governed by distinct forces, each with its own role to play. The strong force stood ready to bind particles together once it was cool enough for them to hold. The weak force waited to govern the slow transformations that would soon set the balance of matter. And gravity, the patient one, had begun the long work of shaping a universe it would not finish for billions of years. Not all of the forces separated at the same moment, and the last parting came later and cooler than the first. 2 of the forces, the one that carries light and the one that governs certain slow transformations of particles, remained joined together as a single force for a while after the others had gone their separate ways. Only when the universe had cooled considerably further did these 2 finally part, settling into the distinct forces we know as electromagnetism and the weak force. That later separation is on firmer ground than the earliest ones because the energies involved are closer to what can actually be studied. The unification of those 2 forces and their parting as the universe cooled has been tested in ways the earliest separations cannot be. It gives confidence in the broader shape of the story, the idea that forces which feel entirely separate today were joined in the heat of the beginning and unfolded one by one as that heat faded. There is a reason physicists came to expect such unification in the first place, and it is a quietly beautiful one. The strengths of the forces are not fixed. They change with the energy at which they are measured, and when that change is followed upward toward higher and higher energies, the strengths of several forces appear to draw together, converging toward a common value. It is as though, at the energies of the early universe, the differences between them would melt away. Each force that separated would go on to play its own role in the long history that followed. The strong force would bind the first protons and neutrons, and later hold together the nuclei of every atom. The force that became electromagnetism would one day bind electrons into atoms and carry every ray of starlight. The weak force would govern the slow transformations that set the balance of matter in the first minutes. And gravity, the patient one, would shape the universe across billions of years. So the separation of the forces was not a loss of something, but an unfolding into something. The universe did not break apart as it cooled. It differentiated, settling from a simple unity into a structured variety, each parting, releasing energy, and adding a new distinction to the world. The richness of the forces we live among is the cooled and settled form of a simpler beginning, the variety that emerged as the first heat drained away. It helps, throughout this story, to remember what temperature really means at these scales. The temperature of the early universe was not warmth in any familiar sense. It was a measure of how fast the particles were moving and how much energy each collision carried. A hotter universe meant particles racing and colliding with greater force. As the universe cooled, the particles slowed and their collisions gentled, and that gentling is what opened each new door in turn. So when we speak of the universe cooling past a threshold, we are describing the particles losing energy as space expands. There is no fire going out, no stove being lowered. There is only the steady thinning and slowing of everything, as the same fixed energy is spread through an ever larger space. The whole sequence of the first minutes is the story of that spreading, and of the doors it opened, one after another. There is a quiet humility in studying a universe no instrument can ever enter. The first instance happened at energies beyond any furnace that could be built, in conditions that can never be fully recreated. And yet the broad shape of them can be reasoned out from the laws that hold today and the traces those instants left behind. We cannot visit the beginning, but we can read it carefully in the language of what it became. But before any of that, one more event would unfold in the first tiny fraction of a second, an event so brief and so consequential that it reshaped the entire universe in less time than thought can measure. The universe was about to stretch. Among all the events of the first fraction of a second, one stands apart for how much it explains. For a brief interval, far shorter than any measure of time the body could feel, the universe is thought to have expanded at a staggering and accelerating rate. It doubled in size, and doubled again and again, growing by an enormous factor in the smallest sliver of an instant. This episode is called inflation, and it set the shape of everything that came after. The numbers involved are beyond ordinary imagining, so it is better to reach for the sense of it. In an interval so short that the mind cannot hold it, a region of space smaller than a single particle was stretched to a size larger than a grain, larger than a world, larger in proportion than almost any comparison can carry. The universe did not drift outward gently here. It was pulled apart at a rate that left it utterly transformed in a flicker. Inflation was first proposed to solve a set of puzzles that had quietly troubled the understanding of the early universe. The first puzzle is the smoothness of things. When the sky is examined on the largest scales, it looks remarkably uniform. Regions on opposite sides of the visible universe, regions that by ordinary reckoning could never have touched or shared anything, nevertheless have almost exactly the same temperature. This is a puzzle, because things that have never been in contact have no reason to match. A sudden early stretch resolves this elegantly. Before inflation, the regions that are now far apart were once pressed close together, near enough to come into balance and settle to a common temperature. Then inflation carried them enormous distances apart in an instant, preserving the sameness they had already reached. The uniformity of the sky is not a coincidence. It is the memory of a time when everything we now see was small enough to touch. Inflation answers other puzzles as well. It explains why the universe appears so evenly balanced in its overall geometry, neither curved sharply one way nor the other, but flat to a remarkable precision. A brief period of enormous stretching naturally flattens whatever it acts upon, the way the surface of any small thing looks flat when it is magnified enough. The large-scale flatness of the cosmos falls out of the same single event. Yet the most beautiful consequence of inflation is also the most important for everything that follows, and it concerns the very smallest scales rather than the largest. On the tiniest scales, the universe is never perfectly still. There is a faint and restless trembling woven into the fabric of space itself, a kind of constant flicker in which tiny disturbances appear and vanish too quickly to last. This jitter is a basic feature of nature at the smallest scales. Inflation took that microscopic trembling and stretched it to enormous size. The tiny flickers, which would otherwise have stayed forever small, were pulled across the growing universe and frozen into it as faint variations in density. Some regions ended up with very slightly more matter than average. Others ended up with very slightly less. The differences were small, almost imperceptible, but they were real, and they were spread across the entire cosmos. Those frozen ripples are the seeds of everything that would ever take shape. The regions with a little more matter pulled in a little more over the long ages that followed, their gravity gathering material toward them. Over hundreds of millions of years, the denser regions grew into the first stars, and then the galaxies, and then the great clusters of galaxies that map the universe today. The largest structures in all of creation are the grown forms of the smallest trembles, magnified in the first instant and never lost. It is worth pausing on the scale of that idea. The pattern of galaxies across the sky, stretching farther than any light has had time to cross, is the direct descendant of fluctuations smaller than a single particle. What was once a quantum whisper became, in time, the arrangement of everything. The map of the cosmos is a portrait of the first instant, enlarged beyond all measure and held in place across billions of years. When inflation ended, the energy that had driven it did not simply vanish. It poured into the universe as a flood of particles and radiation, filling the smoothed and flattened space with intense heat. This is sometimes described as the moment the universe caught fire, a great release of energy that turned a cold and empty stretch into a dense and blazing sea of matter and light. The reheating, as it is called, refilled the universe with the raw material of everything to come. From this point onward, the story moves onto firmer ground. The energies involved, while still far beyond ordinary experience, come closer to the range that physics can study and test. The universe is now a hot, dense sea of fundamental particles, smoothed by inflation, carrying its faint frozen ripples, cooling steadily as it expands. The stage is fully set, and the first true matter is about to take shape. What could possibly have driven such an enormous and sudden expansion is a question with a careful answer. The leading idea holds that space was briefly filled with a peculiar form of energy, a kind of stored energy woven into the fabric of space itself, and that this energy had the unusual property of pushing space to expand rather than letting it settle. As long as that energy held sway, the universe was driven to stretch, faster and faster, until the energy at last released and the stretching ended. This brief stretching also swept the universe clean of certain things it might otherwise have carried. Simpler pictures of the hot beginning predict that the early universe should have produced a scattering of strange and heavy relics, exotic objects left over from the separation of the forces. Yet the universe appears to contain few or none of them. A sudden, enormous expansion explains this neatly, by diluting any such relics so thoroughly across the swelling cosmos that they became vanishingly rare. There is a paradox worth noticing in what inflation accomplished, because it did two opposite-seeming things at once. It smoothed the universe, ironing out differences and making the large-scale cosmos remarkably uniform. And yet it also planted the faint variations that would later grow into all structure. It made the universe both smoother and more textured, smooth on the largest scales and gently rippled on the smaller ones. Both the uniformity and the seeds of structure came from the same brief event. That the idea can be tested at all is part of what gives it weight. The faint variations inflation predicts should have left a particular pattern in the leftover glow that fills the sky, a specific arrangement of slightly warmer and slightly cooler regions, with characteristic sizes and proportions. When that glow is measured in fine detail, the pattern found within it matches the prediction closely. The seeds of structure, frozen in the first instant, can be read in the sky today. It is worth holding, one more time, the sheer reach of what this means. The arrangement of galaxies across the sky, the great pattern of clusters and the quiet gaps between them, is the grown form of fluctuations, smaller than a single particle, stretched across the universe in a flicker and never lost. The map of the cosmos is, at its root, a portrait of the first instant. What was once a faint quantum trembling became the shape of everything. It is worth holding how brief inflation was against how much it accomplished. The interval lasted a tiny fraction of the first second, far too short for any sense to register, and yet in that flicker, the universe was transformed beyond recognition. A region too small to see was stretched larger than imagining, smoothed, flattened, and seeded all at once. The longest consequences of the cosmos were set in its very shortest moment. There remains genuine work to be done in understanding inflation fully, and that openness is part of its character. The broad idea explains a remarkable range of things with a single stroke, and its predictions for the pattern in the sky have held up well. Yet exactly what drove it and how it began and ended are questions still being worked out. The picture is strong and well tested at its edges, and honest about the frontier that remains at its center. And so, we leave the sudden stretch behind. In less time than any instant the senses could register, the universe was smoothed, flattened, and seeded with the patterns of all its future structure, then filled with fire. Everything that follows, every star and every world, traces back to the faint variations planted in that flicker. We turn now to the sea of particles it left behind, and to the first pieces of ordinary matter forming within it. After inflation, the universe was an extraordinarily hot and dense sea of the most basic particles that exist. They moved at tremendous speeds and collided without rest, and the energy of those collisions was so great that matter and light were barely distinct from one another. Energy turned into particles, and particles turned back into energy, in a constant churning exchange that filled all of space. Among the particles in this sea were quarks, the tiny constituents that, in the universe we know, are always locked away inside larger particles. In the present cosmos, a quark is never found alone. It is always bound together with others, hidden inside the protons and neutrons that make up the nucleus of every atom. But in the first fraction of a second, the quarks were not yet bound. The universe was simply too hot to hold them together. Anytime three quarks began to gather into a proton or a neutron, the violence of the surrounding collisions broke them apart again at once. The particles that would later form the solid core of all matter could not yet endure. They existed only as free quarks, racing through the hot sea, unable to settle into anything lasting. This state is often called the quark sea or the quark soup, a universe filled with unbound pieces. Alongside the quarks moved the particles that carry the strong force, the messengers that would later bind quarks together once it was cool enough. There were also countless other particles in the mix, along with their mirror partners, all flickering into and out of being as the energy of the universe converted itself ceaselessly from one form to another. It was a sea with no surface and no shore, blazing in every direction at once. There is an image worth holding here, and it is one of the strangest features of the early universe. There was no darkness anywhere. In the cosmos we know, space is mostly dark, with scattered points of starlight against a black background. But in the first moments, the whole of space was filled with light and matter so densely that there was no dark to be found. The universe did not contain light. The universe was light, glowing uniformly from edge to edge. As the universe expanded, it cooled, and here again cooling is the quiet force moving everything forward. Nothing strikes the quark sea to change it. It changes only because the temperature falls as space stretches, and because falling temperature opens doors that were closed before. The whole of this story is paced by that steady cooling, a universe passing through one threshold after another, simply by growing larger and colder. Within this hot sea, one quiet and profound threshold was crossed, and it concerns the very property we think of as weight. There is a field that fills all of space, present everywhere, and it is this field that gives many particles their mass. Above a certain temperature, many of the most basic particles behaved as though they had no weight at all, racing along at the speed of light, unable to slow down. As the universe cooled past a particular point, those particles began to interact with this all-pervading field, and in doing so, they gained mass for the first time. The weight of a particle, it turns out, is not something built into it from the very beginning. It is a property that emerged as the universe cooled, a feature that only appeared once the temperature had fallen far enough for it to exist. Before that threshold, the idea of weight had no meaning. After it, particles had the masses they carry still. This is a subtle thing, and it rewards a slow consideration. The mass of a particle, the resistance it offers when pushed, the pull it feels from gravity, all of this came into being at a moment in the first fraction of a second, as a consequence of cooling. The universe did not start with weight already woven into its particles. Weight settled into them, the way frost settles onto a surface only when the air has grown cold enough. With that threshold crossed, the particles of the universe now carried the masses they would keep. The quarks were still unbound, still racing free in the cooling sea, but the conditions that would let them join together were drawing near. Every moment, the universe grew a little larger and a little cooler, and with every drop in temperature, the sea moved closer to the point where the first durable matter could form. For now, picture the universe as it was, a sea of unbound particles blazing in every direction, with no dark place anywhere and no solid thing yet made. It is cooling, always cooling, and as it cools it is approaching a threshold that will give it its first lasting pieces. The quarks are about to be captured, bound together into the particles that will still exist, essentially unchanged, inside every atom of every later age. Something close to this hot sea has been glimpsed, faintly and briefly, in careful work on the ground. When particles are driven together at tremendous energies, they can be made to form, for the smallest flicker of time, a tiny droplet of matter in much the state the early universe was in, with the quarks briefly unbound. It is the faintest reflection of those first moments, made to appear and vanish in an instant, and it behaves as the early universe should have behaved. The density of the early sea is difficult to imagine, because nothing in ordinary life approaches it. The whole of the matter that would later make a star, a galaxy, a great cluster of galaxies, was packed into a space unimaginably small and hot. Particles were so close and so energetic that they collided without rest, and the distinction between matter and light blurred in the constant exchange of one into the other. That exchange ran in both directions, ceaselessly. Energy gathered itself into particles, and particles met and dissolved back into energy throughout the whole of the sea. There was no settled population of matter yet, only a churning balance of creation and destruction, held steady by the heat. The universe was less a collection of things than a process, a continual turning of energy into matter and back again. Among the particles carrying the strong force through this sea were the messengers that bind quarks together, and in the heat, they were as free and unbound as the quarks themselves. They would later become the glue of every proton and neutron, the carriers of the force that holds all nuclei together. But for now, they raced freely through the sea, part of the churning crowd, waiting for the cool that would let them do their binding work. The field that gives particles their mass deserves one more slow thought, because its threshold is among the strangest in the story. Before the universe cooled past a certain point, this field had not yet settled into its present form, and so the particles moving through it felt no weight at all. The settling of that field, as the universe cooled, was the moment weight entered the world, the moment the particles of matter first felt the resistance and the pull that mass brings. At the root of all this churning lay a single principle, that matter and energy are two forms of one thing. Energy can gather itself into particles of matter, and matter can dissolve back into energy, and the exchange rate between them is fixed by nature. In the heat of the early universe, this exchange ran constantly and in both directions, so that the line between matter and light was not sharp but fluid, a continual trading of one form for the other. This is why the early universe could make matter at all. The energy of the hot sea was so great that it poured itself into particles as fast as those particles dissolved, filling the cosmos with a population of matter drawn directly out of energy. As the universe cooled, the trade slowed, and the particles that remained were those that had survived the cooling rather than dissolving away. The matter of the world was, quite literally, congealed energy, settled out of the hot beginning. There is a simple wonder in holding that thought. Every solid thing, every particle with weight, began as energy that gathered into form as the universe cooled. The substance of the world is not separate from the light of the beginning. It is that light, slowed and settled into matter, carried forward through all the ages since. The hot sea did not contain matter so much as become it, a little at a time, as it cooled. But before the first matter could be made and kept, the universe had to settle a strange and profound imbalance, a near-perfect cancellation that came within a hair of leaving the cosmos empty. We turn now to one of the most consequential events of the first second, the great meeting of matter and its opposite. One of the most profound events of the first second concerns a strange and delicate imbalance, and it touches on the simplest and largest question of all, which is why there is something rather than nothing. In the hot, early universe, energy was constantly converting into pairs of particles. For every particle of ordinary matter that formed, a matching particle of the opposite kind formed alongside it. That opposite kind of matter is real, and it is well understood. For nearly every type of particle, there exists a partner with the same mass but an opposite electric charge, a kind of mirror image. When a particle meets its mirror partner, the two do not simply collide and bounce away. They annihilate one another completely, vanishing entirely, and converting all of their mass back into light. This is not rare or exotic. It is a basic feature of how matter and its opposite behave. In the first instance, matter and its mirror were created and destroyed in enormous and nearly equal numbers. Pairs formed from energy, and pairs met and annihilated back into energy, over and over, throughout the whole of the hot sea. As long as the universe stayed hot enough, this cycle continued, with creation and destruction nearly balanced and the population of particles holding roughly steady. Now consider what would have happened if the balance had been perfect. If matter and its mirror had been created in exactly equal numbers, then as the universe cooled, every particle would eventually have found its partner, and every pair would have annihilated. The cosmos would have ended this chapter as a sea of light with no matter in it at all. There would be no stars, no worlds, no atoms, no observers. The universe would have cancelled itself out completely. But the balance was not perfect. For reasons that are still not fully understood, matter very slightly outnumbered its mirror by only about 1 part in a billion. For roughly every billion mirror particles, there were about 1,000,000,001 particles of ordinary matter. The excess was almost absurdly small, a single extra particle among 1,000,000,000 pairs, and yet that tiny surplus made all the difference. When the great annihilation came, and the universe cooled to the point where the pairs could no longer be replaced, nearly everything paired off and vanished into light. The matter and the mirror found one another and cancelled, particle by particle, until almost nothing was left. But not quite nothing. That tiny excess of ordinary matter, the 1 part in 1,000,000,000 that had no partner to annihilate against, was left behind. It survived. Everything made of ordinary matter traces back to that thin residue. Every atom in every star, every grain of dust drifting between the worlds, every stone and every sea, and every living body is built from the 1 in 1,000,000,000 remainder that escaped the great cancellation. The universe came within a hair of erasing itself entirely, and the narrow margin by which it failed is the reason that anything exists at all. We are the survivors of a near-perfect undoing. The annihilation left a second legacy as well, and it is one we can still measure today. All of those vanished pairs became light, an immense flood of it, and that light did not disappear. It still fills the universe, cooled and stretched by the long expansion of space into a faint glow that bathes the entire sky from every direction. For every single particle of matter that survived, there are roughly 1,000,000,000 of those leftover particles of light. That ratio is a fossil of the great cancellation, preserved across the whole history of the cosmos. 1,000,000,000 grains of light for every grain of matter, spread evenly through all of space, a direct record of how close the universe came to leaving nothing behind. When that faint glow is measured today, it carries within it the memory of the moment when almost everything annihilated, and a sliver of matter was spared. Why matter prevailed over its mirror remains one of the genuinely open questions in physics, and it is worth holding it honestly as the open question it is. The general conditions that could produce such an imbalance can be described in broad terms, but no complete and confirmed explanation yet exists. We know that the imbalance happened because we are here, made of the matter it left behind. We do not yet fully know why. There is a quiet wonder in sitting with that uncertainty rather than rushing past it. The existence of everything rests on a tiny asymmetry whose cause is still being sought. Had the numbers been exactly even, the cosmos would be empty light. Had the excess been larger, the universe would look very different. The thin and unexplained margin that favored matter is the reason for stars, for worlds, and for the quiet thought considering it now. The conditions required for matter to outlast its mirror can be stated in general terms, even if the full explanation is still missing. The universe must treat matter and its mirror at least a little differently rather than perfectly evenly. It must allow a certain reaction that does not balance out, and it must pass through these conditions while it is out of balance overall, as a cooling, expanding universe always is. The early cosmos seems to have met these conditions, but exactly how remains unsettled. Mirror matter is not only a feature of the early universe. It is made and studied in small amounts today, carefully created and held for the briefest moments before it meets ordinary matter and annihilates. Its behavior is examined closely for any tiny difference from ordinary matter, any faint asymmetry that might hint at why the early universe favored one over the other. Small differences have been found, but not yet enough to fully explain the imbalance that left a universe full of matter. The ratio of light to matter left by the Great Cancellation is not a vague figure, but a measured one. When the faint glow that fills the sky is studied alongside the amount of ordinary matter in the cosmos, the proportion comes out to roughly 1 billion particles of light for every particle of matter. That number is a direct count of the survivors, a measure of how nearly complete the cancellation was, preserved in the sky for anyone who cares to read it. There is a way of putting it that stays with you. Nearly all of the matter that ever formed was annihilated, turned to light, and that light is the faint glow that still fills the universe. Ordinary matter, everything solid and lasting, is the thin remainder that escaped. In a real sense, the substance of the world is what was left over after almost everything cancelled, and the sky still glows with the light of all that vanished. It is worth sitting with how improbable our own existence appears from this vantage. Had the imbalance been absent, the universe would be empty light, with no matter to gather into anything. Had it been far larger, the cosmos would look entirely unlike the one we know. The thin and still unexplained margin that favored matter, 1 part in 1 billion, is the reason there are stars to form, worlds to gather, and quiet minds to wonder about the margin at all. It is humbling to think that the question behind all of this is the simplest one a child might ask, which is why there is anything here at all. The Great Cancellation is the moment that question was answered, not in words, but in fact, by a margin so slight it can scarcely be pictured. 1 extra particle in 1 billion is the whole of the reason for substance. Everything that has weight and lasts is the answer the universe gave to that simplest question. And the answer came without ceremony, in the ordinary cooling of an expanding universe. There was no special intervention, no grand exception, only the quiet working out of physics in a cosmos that happened to favor matter by the faintest degree. The profound and the ordinary meet here, in a small imbalance that decided whether the universe would be full or empty. It was full by the thinnest of margins, and so the story could continue. With the Great Cancellation complete, the universe was left with its small surplus of ordinary matter and its enormous sea of light. The quarks of that surviving matter were still unbound, still racing through the cooling cosmos. But the temperature was falling toward the point where they could at last be captured, and the first durable particles of matter were about to take shape. We turn now to the forging of the first true building blocks. Around 1/1,000,000th of a second after the beginning, the universe had cooled to a temperature of a few trillion degrees. This was still hotter than the core of any star that would ever exist, hotter than anything in the present cosmos. And yet, by the standards of the first instant, it was cool at last, cool enough for something new and lasting to take shape. The quarks, which had roamed free in the hot sea, could finally bind together. In groups of 3, the quarks locked into the particles that would become the foundation of all ordinary matter. These are the protons and the neutrons, the particles that sit at the core of every atom in the universe. A proton is a bundle of 3 quarks carrying a positive electric charge. A neutron is a similar bundle of 3 quarks, but with no overall charge, balanced and neutral. Once formed, in this cooler universe, they could endure. This was a threshold of real significance. The protons and neutrons forged in that first millionth of a second are, in a sense, still here. The protons especially have lasted, essentially unchanged, from that moment to this one. The proton at the center of a hydrogen atom in a glass of water tonight may well have been made in the first millionth of a second of the universe and kept ever since. The building blocks were cast almost at the very beginning. The building came much later. It is worth being clear about what existed at this stage and what did not. There were no atoms yet, and no nuclei in the full sense. There was only a hot, dense gas of these freshly made protons and neutrons mixed together with electrons, with the surviving particles of light, and with the elusive particles called neutrinos that we will come to shortly. The universe was a glowing fog of simple pieces, not yet assembled into anything we would recognize. Protons and neutrons are close cousins, nearly identical, but not quite. A neutron is very slightly heavier than a proton. The difference is tiny, a fraction of a percent in mass, and at first it seems like a detail too small to matter. Yet that tiny difference in weight will turn out to shape the entire composition of the universe a few minutes later. In the early cosmos, the smallest differences are the ones that last longest, and this one runs through all of chemistry. In the heat of the early universe, protons and neutrons were not fixed in their identities. They readily transformed into one another, a proton becoming a neutron becoming a proton, through reactions involving the lighter particles that surrounded them. As long as the universe stayed hot enough, this back and forth ran freely in both directions, and the two kinds of particle existed in nearly equal numbers, each constantly turning into the other. So picture the universe at this moment as a balanced exchange. Protons turn into neutrons as often as neutrons turn into protons, and the population of each holds roughly even. There are about as many neutrons as protons, all of them newly made, all of them mixed into the hot fog of light and lighter particles. The universe has its first durable matter, and for the moment, that matter is evenly divided between its two forms. But this balance depends entirely on the heat, and the heat is fading. The reactions that keep protons and neutrons turning into one another require the energy of a very hot universe. As the cosmos continues to cool, those reactions will begin to slow, and the delicate balance between the two kinds of particle will start to tip. The slight extra weight of the neutron, so easy to overlook, is about to assert itself. For now, though, the universe has crossed a quiet milestone. It has made its first lasting pieces, the protons and neutrons that will still be present, unchanged, in every atom of every star and every world to come. The bricks of ordinary matter exist. They are not yet joined into anything, not yet gathered into nuclei or atoms, but they are made, and they will keep. The hardest part of building matter, in a sense, is already behind the universe. What remains is assembly, and assembly will take time. The protons and neutrons must wait through the next stages, as the universe cools further and the conditions change. They must survive the tipping of the balance between them. And they must wait for the temperature to fall to the narrow point where they can at last be bound together into the first nuclei without being broken apart again by the surrounding light. There is a reason quarks are never found alone in the present universe, and it explains why they could only bind once things had cooled. The strong force that acts between quarks behaves unlike any force of ordinary experience. It does not weaken with distance the way gravity or magnetism do. Instead, it holds firm, and any attempt to pull two quarks apart only meets greater resistance, so that a lone quark cannot persist. The quarks must be bound, three together, into balanced and stable groups. In the heat of the first instance, the particles collided so violently that even this firm binding could not hold, and the quarks were knocked apart as fast as they gathered. Only when the universe cooled to a few trillion degrees did the collisions soften enough for the binding to win. Then the quarks settled, three to a bundle, into the protons and neutrons that would endure. The strong force, which had been unable to do its work in the heat, finally locked the first matter into place. The protons made in that moment are remarkable for how long they last. As far as anyone has been able to determine, a proton is essentially stable, enduring without change across spans of time that dwarf the present age of the universe many times over. The proton at the center of a hydrogen atom in a glass of water has, in all likelihood, existed since the first millionth of a second. Few things in nature are so nearly permanent. Mixed into the hot fog alongside the protons and neutrons were the electrons, the light and negatively charged particles that would one day complete the first atoms. For now, they were far too energetic to be captured and held by any nucleus, and so they roamed free, part of the churning crowd. They would have to wait a very long time, hundreds of thousands of years, before the universe cooled enough for them to settle onto nuclei and form whole atoms. The reactions that turned protons into neutrons and back again ran through the lighter particles of this crowd, the electrons and the neutrinos, and their mirror partners. A proton could absorb one of these and become a neutron. A neutron could emit one and become a proton. As long as the fog was hot and dense, these exchanges ran freely in both directions, keeping the two kinds of particle in their near-even balance. The fate of that balance was tied to the lighter particles, and those particles were about to depart. There is a quiet surprise hidden inside the proton, and it is worth a slow moment. The three quarks that make up a proton account for only a small part of its weight. Most of a proton's mass comes not from the quarks themselves, but from the energy of the strong force that binds them, the ceaseless churning of the force that holds them together. The weight of ordinary matter is, in large part, bound energy, the stored vigor of the force that locks the quarks in place. This means that the heft of everything solid traces back, once again, to energy rather than to substance. The mass of a stone, of a star, of a body is mostly the energy of the strong force humming inside its protons and neutrons. The first building blocks made in that early millionth of a second carried this hidden truth from the start, that what feels like solid matter is, at its core, energy held in a tight and lasting balance. As the universe approached 1 second of age, it was thinning and cooling toward exactly such a change. The hot fog of particles was growing less dense, the reactions were beginning to falter, and one kind of particle in particular was about to part ways with all the rest. The neutrinos, the faintest and most elusive of all, were about to be set free. We turn now to the moment, around 1 second, when the ghosts of the early universe began to stream into the dark. At about 1 second after the beginning, with the universe cooled to roughly 10 billion degrees, one of the most abundant kinds of particle in the cosmos quietly went its own way. These are the neutrinos, and they are among the strangest and most retiring of all the particles of nature. They are extraordinarily light. They carry no electric charge, and they barely interact with anything at all. To understand how little neutrinos engage with the rest of matter, consider the present universe. Countless neutrinos stream through every living body each second, passing through flesh and bone and the solid ground beneath, as though none of it were there. They pour out of the core of the closest star in uncountable numbers, and nearly all of them cross the entire body of a planet without once touching anything. They are almost, but not quite, untouchable. In the dense early universe, however, even neutrinos were packed so tightly that they collided constantly with everything around them. The fog of particles was thick enough that even these elusive ghosts could not slip through it freely. They were bound up with the rest of the hot matter, scattering and interacting, part of the single churning sea. For the first second, the neutrinos were held within the crowd. As the universe expanded and thinned, the neutrinos reached a turning point. The matter around them grew sparse enough that collisions became rare, and then rarer still, until at last the neutrinos essentially stopped interacting altogether. They decoupled, parting from the rest of the universe, and began to travel freely through space in whatever direction they were already moving. From that second onward, they have been streaming outward without pause. Those neutrinos are still here. A sea of relic neutrinos, set loose in the first second of the universe, fills all of space to this day. They are older than starlight, older than atoms, older even than the first nuclei that had not yet formed when they were freed. They have been traveling for more than 13 billion years, cooling as the universe expands, a faint and almost untouchable record of the universe's first heartbeat. This relic sea has never been directly detected, and the reason is exactly the property that defines neutrinos. They interact so weakly that catching even the energetic ones is a difficult feat, and these relic neutrinos are extraordinarily cold and gentle, far harder to sense than any others. And yet there is little doubt that they are present, because their influence is woven quietly into the rest of the story. The universe behaves precisely as it should if that sea is there. In a sense, the relic neutrinos are the oldest fossil of all, a record from a time before even the first nuclei. The faint glow that fills the sky comes from a much later age, hundreds of thousands of years after the beginning. The relic neutrinos were set free in the first second. They carry within them, untouched, the imprint of a moment no instrument will ever photograph, streaming silently through everything that has been built since. With the neutrinos gone their own way, a quiet consequence began to unfold among the protons and neutrons left behind. The gentle back and forth that had kept the two kinds of particle in balance depended on reactions involving exactly these lighter particles. As the neutrinos decoupled and the universe cooled, those reactions began to falter, and the balance between protons and neutrons started to shift. Recall that the neutron is very slightly heavier than the proton. Because of that small extra weight, it costs a little more energy to make a neutron than to make a proton. In a very hot universe, energy is plentiful and the difference hardly matters, so the two stay roughly even. But as the universe cooled, that small extra cost began to weigh more heavily, and the reactions increasingly favored the lighter particle. Protons began to outnumber neutrons. The balance tipped gently but steadily. Where once there had been about as many neutrons as protons, now the neutrons began to fall behind. With every drop in temperature, it became a little harder to make a neutron and a little easier to make a proton, and the proportion of neutrons in the universe quietly declined. The slight difference in weight between two particles was beginning to write itself into the composition of all matter. This shifting balance is one of the most consequential things happening in the early universe, though it unfolds without any drama at all. It is simply a matter of energy and cooling, of a small weight difference made to matter by a falling temperature. And the precise point at which the balance settles will determine, a few minutes later, exactly how much helium the universe is able to make. The recipe of the cosmos is being set here, quietly, by arithmetic. Soon after the neutrinos departed, another quiet event warmed the rest of the universe a little. The electrons and their mirror partners, which had been present in great numbers, met and annihilated as the universe cooled past the point where they could be replaced. Their annihilation poured energy into the sea of light, warming it slightly. But the neutrinos had already gone their own way, and so they did not share in that warming. To this day, the relic neutrinos are a touch cooler than the leftover glow of light, a small and lasting mark of the order in which things happened. The relic neutrinos that fill space today are extraordinarily gentle, cooled by more than 13 billion years of expansion to a whisper of their former energy. This is part of why they have never been caught directly. The energetic neutrinos that pour from stars are hard enough to sense, and these relic neutrinos are far fainter still, slipping through everything without a trace. They are perhaps the most elusive thing in all the cosmos, and also among the most numerous. And yet, their presence is not in doubt, because the universe carries their mark. The faint glow that fills the sky has a particular pattern woven through it, and the fine details of that pattern depend on how much the relic neutrinos weighed in upon the early universe. When that pattern is measured, it fits exactly what it should if the sea of neutrinos is there. The amount of helium the universe made depends on them as well, and it too comes out right. So the relic neutrinos are read not by catching them, but by their influence, the way a current is read, by the drift of everything it carries. They are written into the glow of the sky and into the proportions of the simplest elements, present in both records exactly where the story places them. The oldest fossil of all is invisible, and still its fingerprints are everywhere, pressed quietly into the universe that grew up around it. There is a strange comfort in knowing that something so ancient is still streaming through everything tonight. The relic neutrinos set loose in the first second have never stopped traveling. They pass through the body, through the ground, through the whole of a planet, carrying within them the imprint of a moment before the first nuclei, before the first atoms, before anything we would recognize. The first second of the universe is still passing through the room, gently and without a sound. There is something delicate in the fact that a neutron is heavier than a proton at all, and by just the amount that it is. Had the difference been larger, neutrons would have grown scarce far sooner, and the universe would have made little helium. Had the difference been smaller, neutrons would have lingered, and the universe would have come out far richer in helium, with less hydrogen left over for the stars and the seas. The recipe of matter rests on a tiny margin of weight. So the composition of everything was being decided, in these seconds, by quantities almost too small to picture: the faint extra weight of one particle over another, the gentle pace of cooling, the slow ticking of neutron decay. None of it was loud or sudden. It was arithmetic, worked out quietly in a cooling universe, and its answer would shape every star and every world that would ever form. The grandest outcome followed from the smallest of differences. By the time the reactions effectively shut off, a moment we will come to next, the balance had reached roughly 1 neutron for every 5 protons. This number, born from the weight of a particle and the rate at which the universe cooled, is one of the most important quantities in the whole of the story. We turn now to the moment it settled, and to the slow loss of neutrons in the minutes that followed. As the universe continued to cool past 1 second, the reactions that turned protons and neutrons into one another grew slower and slower, until they essentially stopped. This moment is often called the freeze-out, and the name captures it well. The proportion of neutrons to protons, which had been shifting steadily as the universe cooled, now became fixed, frozen in place because the reactions that could change it had faded away. At the moment of freeze-out, the universe held roughly 1 neutron for every 5 protons. This ratio was not chosen by anything. It was the simple outcome of 2 facts working together: the slight extra weight of the neutron and the rate at which the universe was cooling. Had the neutron been a little heavier, or the cooling a little faster, the number would have come out differently, and the universe would have a different composition today. But the story of the neutrons does not end at freeze-out, because a free neutron is not a stable thing. A neutron locked inside a nucleus can last essentially forever, but a neutron left on its own, drifting freely, will not endure. Over a span of about 10 minutes, a lone neutron will transform itself, decaying into a proton and lighter particles. This is a basic and unavoidable feature of how neutrons behave when they are not bound up with anything. So in the minutes after freeze-out, as the universe waited for the next threshold, the free neutrons were quietly decaying away. One by one, neutrons turned themselves into protons, and the proportion of neutrons in the universe, already small, grew smaller still. The balance drifted further toward the proton, falling from about 1 in 5 toward roughly 1 in 7. The clock was running, and the neutrons were slowly being spent. There is a quiet tension in this stage of the universe, though it unfolds in perfect silence. The neutrons can only be saved from decay by being locked inside a nucleus, sheltered there from the transformation that would otherwise claim them. But they cannot yet be locked into anything, because the universe is still too hot for nuclei to hold together. So the neutrons wait, and as they wait, their numbers slowly dwindle. The universe, in effect, is caught in a race against its own cooling. If it cools too slowly, the neutrons keep decaying, and few will be left to build with. If the conditions were somehow to change too fast, there would be no time for the building to happen at all. Everything depends on the timing of the next few minutes, on the narrow window between a universe too hot to form nuclei and a universe too cool and too sparse for the reactions to run. It is worth dwelling on how much rests on this delicate timing. The amount of helium the universe will make depends directly on how many neutrons survive to be built into it. Every neutron that decays before it can be sheltered is a neutron loss to the building. And so the slow loss of neutrons in these minutes, quietly ticking down, is shaping the chemistry of every star and every world that will ever exist. The reason the neutrons cannot yet be saved brings us to the central obstacle of the first 3 minutes. To lock a neutron safely into a nucleus, the universe must first take a single step, the binding of one proton and one neutron together. That first pairing forms a particular kind of nucleus, the simplest one beyond a lone proton, and it is the doorway through which all the building must pass. Yet that doorway, for now, keeps slamming shut. This is the great delay of the early universe, and it explains why the story is one of minutes rather than fractions of a second. The protons and neutrons are present and ready. The temperature has fallen enough for them to exist. And still the universe can make no real progress in building nuclei, because the very first step keeps undoing itself in the surrounding heat. The materials are in hand, and the door is held shut by the light. So as the neutrons slowly decay and the universe slowly cools, everything waits on a single threshold. The cosmos must cool just enough that the first fragile pairing can survive long enough to lead onward. Until then, the universe holds its breath, its building materials ready, its neutrons dwindling, its great construction stalled at the very first rung. We turn now to that obstacle itself, the bottleneck that made the universe wait. It is a curious thing to consider that the universe spent its first minutes not building, but waiting to build. The dramatic separations of the forces, the sudden stretch, the great cancellation, all of these had already happened in the first second. And now, with its first matter made and its balance set, the universe simply waited, cooling, for permission to take the next step. That permission would come at the end of a fragile and frustrated delay. The idea of freeze-out is worth understanding gently, because it governs so much of what happens here. A reaction can only keep two populations in balance if it runs faster than the universe is changing around it. As the cosmos expands and cools, the reactions slow, and at some point they can no longer keep pace with the expansion. When that happens, the balance they were maintaining simply stops where it is, frozen, because nothing can shift it any longer. The neutron-to-proton ratio froze in exactly this way. The lifetime of a free neutron sets the pace of the slow loss that follows. Left to itself, a lone neutron lasts about 10 minutes before it decays, and the first 3 minutes are a fair fraction of that span. So as the universe waited at the bottleneck, a meaningful share of its free neutrons quietly transformed into protons. The timing of the building, then, was a matter of real consequence. A longer wait would have meant fewer neutrons and a different universe. It is interesting to consider how sensitive the outcome was to the details. If the neutron had not decayed at all, more of them would have survived to be built into helium, and the universe would have come out richer in helium than it did. If the universe had cooled faster or slower, the freeze-out ratio itself would have shifted. The composition of all ordinary matter rests on these fine balances: the neutron's slight extra weight, its lifetime, and the rate of cooling, all working together. The rate of cooling, in turn, depended on what filled the early universe, on how many kinds of particle were present to share its energy. A universe crowded with more kinds of particle would have cooled at a different pace, and frozen its balance at a different point, and made a different amount of helium. The quarter of helium we measure today is, in this way, a record of the contents of the universe in its first seconds, written into the proportions of the simplest matter. So the few minutes of waiting were not idle. They were a finely poised interval in which the neutron supply slowly drained, the temperature slowly fell, and the moment of building drew nearer. Everything depended on these two slow processes, meeting at the right point, on the universe cooling enough to build before too many neutrons were lost. The whole recipe of the cosmos was being decided, quietly, by the patience of those few minutes. It is a remarkable thought that the helium of the cosmos can be used to weigh the contents of the first second. Because the amount of helium depends on how fast the universe cooled, and the cooling depends on how many kinds of particles shared the early heat, the measured helium becomes a way of counting those early particle types. The quarter of helium found across the sky agrees with a particular small number of fundamental particle families and no more. This is a quiet marvel of the whole picture, that something as ordinary as the helium in the air carries a record of the deepest contents of the first second. The first 3 minutes in setting the recipe of matter also pressed into that recipe a count of what the universe was made of at the start. To read the helium of the oldest gas is, in a sense, to take a census of the early cosmos, taken when the universe was barely a second old. The obstacle has a name drawn from the very nucleus that kept dissolving, and understanding it is the key to understanding why the first nuclei formed when they did, and not a moment before. We turn now to the bottleneck, and to the patient wait that finally ended around the 3-minute mark. To build any nucleus heavier than a single proton, the universe needed to take one particular first step. It had to bind one proton and one neutron together into a single nucleus. This pairing forms a heavy form of hydrogen, a nucleus made of just 2 particles, and it is the essential first rung on the ladder of all element building. Without it, nothing heavier can form, because every path upward runs through it first. This simplest of compound nuclei is the doorway to everything that follows. Once a proton and neutron are joined, that pair can gather more particles and climb toward heavier and more stable forms. But the climb cannot begin until the first pair is made and holds. And here lay the great obstacle of the early universe, the reason the first 3 minutes were minutes at all rather than an instant. The trouble is that this first nucleus is held together only loosely. The bond between the proton and the neutron in this particular pairing is weak compared to the bonds in heavier nuclei. And in the intense radiation that still filled the early universe, the light itself carried enough energy to break that fragile bond apart. A passing particle of light would strike the newly formed pair and knock it back into a separate proton and neutron almost the instant it formed. So the universe was caught in a frustrating cycle. A proton and a neutron would find one another and join. A particle of light would immediately strike them and break them apart. They would join again and be broken again, over and over, with no lasting progress. The first rung of the ladder kept dissolving as quickly as it was built. This obstacle is known as the bottleneck, named for the fragile nucleus that could not yet survive. And so, even though the protons and neutrons were present and willing to combine, the universe could make no headway. The delay was not caused by any shortage of materials. The building blocks were all in place. The delay was caused by the heat, by the energy of the light that shattered each new pairing the moment it formed. The universe had to wait, not for particles, but for the temperature to fall far enough that the light could no longer break the bond. This is the quiet center of why the first 3 minutes unfolded as they did. The ingredients were ready almost immediately, within the first second. But the heat held the door shut, and the whole sequence had to be paced by cooling. The universe waited, with its building materials in hand, for the temperature to drop low enough to give permission. Only then could the bottleneck open, and the building finally begin. The threshold the universe was waiting for lay at a temperature of about 1 billion degrees. Above that point, the light was energetic enough, on average, to keep splitting the fragile pairing apart. Below it, the light at last grew too gentle to do so, and the first nucleus could survive long enough to lead onward. That threshold was reached gradually, near the end of the first minute and into the third, as the universe cooled toward it. It is worth holding the strangeness of this delay in mind, because it shapes the whole character of the beginning. The universe was not building furiously in its first moments. It was waiting. The protons and neutrons drifted in the cooling fog, occasionally pairing and being broken apart, while the neutrons among them slowly decayed and the temperature inched downward. The grand construction of matter was stalled at its very first step, held there by the warmth of the universe itself. And as the universe waited, the stakes quietly rose. Every minute that passed, more free neutrons decayed into protons, and the pool of neutrons available for building grew smaller. The longer the bottleneck held, the fewer neutrons would remain to be locked into nuclei when the door finally opened. The delay was not only a pause. It was a slow draining of the very material the universe was waiting to use. There is a kind of balance written into this, a poised and patient tension. The universe could not build too early, because the heat would have shattered everything it made. But it could not afford to wait too long, because its neutrons were steadily slipping away. The window for building nuclei was set by these two pressures together, the heat pushing the start later and the decay of neutrons demanding it not come too late. When the temperature finally fell past the critical point, near the 3-minute mark, the bottleneck began to open. The light at last grew too gentle to break the fragile first nucleus, and the proton-neutron pairing could survive. And once that first rung could hold, everything changed quickly. The patient waiting of the early universe was about to give way to a brief and decisive burst of building, the only such episode the cosmos would manage on its own. The fragility of that first nucleus comes down to how loosely it is bound, and the number is part of why the wait was so long. The bond holding the proton and neutron together in this simplest pairing is far weaker than the bonds in heavier nuclei. It takes only a modest amount of energy to break it, and in the early universe such energy was everywhere, carried by the abundant light. The first rung of the ladder was the most fragile one, and it had to be crossed before any other. The enormous number of light particles made the obstacle worse than temperature alone would suggest, and this is a subtle and lovely point. Recall that there were roughly 1 billion particles of light for every particle of matter. Even after the average light had cooled below the energy needed to break the fragile nucleus, a small fraction of the light still carried more than its share. And with 1 billion particles of light for every nucleus, even that small fraction was enough to keep splitting the pairings apart. The universe had to cool well past the simple threshold before the building could begin. So the sheer abundance of light held the door shut longer than one might expect. The bottleneck did not open the moment the average particle of light grew too gentle. It opened only when even the rare energetic stragglers among that billion-to-one sea had faded enough to leave the fragile nucleus in peace. This is part of why the building waited until the 3rd minute rather than the 3rd second, the great crowd of light enforcing patience long after the average had cooled. When the threshold finally came, at a temperature of about 1 billion degrees, the change was not gradual, but rather quick. Below that point, the fragile nucleus could endure, and once it could endure, the reactions that had been stalled for minutes were free to proceed. The door that had been held shut for so long swung open in a relatively brief span, and the long-delayed building of nuclei began all at once across the whole universe. There is a quiet beauty in how the long wait gave way to a sudden burst. For minutes, the universe had drifted, its materials ready, its first step undone, again and again, by the light. And then, as the cooling crossed a single threshold, the frustration lifted and the building came in a rush. The patience of the early universe was real, but it was not endless. It ended, all at once, around the 3-minute mark. It is worth noticing that most of the first 3 minutes were spent waiting rather than building. The separations, the stretch, the cancellation, the forging of the first particles, all of these were finished within the first second. The remaining minutes were largely a patient pause, a universe drifting and cooling with its materials in hand, held at the threshold by its own warmth. The great construction was brief. The waiting before it was most of the span. There is a certain calm in that picture, of a universe in no hurry, even at its most consequential hour. It did not rush to build. It cooled at its own steady pace, and it built only when the cooling allowed, not a moment before. The first 3 minutes were not frantic. They were patient, even slow, a beginning that took its time and could not be hurried, settling toward its one brief act of making. We come now to the moment the thumbnail points toward, the universe at roughly 180 seconds old, the bottleneck swinging open, and the first true nuclei forming at last. After the long wait, the building begins, and it begins all at once. We turn now to the forging of the first nuclei, the brief cosmic fire that lit, burned, and went out within the span of a few minutes. When the temperature of the universe finally fell past the critical point, the bottleneck opened, and the change came quickly. The simplest compound nucleus, the pairing of one proton and one neutron, could now survive without being broken apart by the surrounding light. And once that first rung of the ladder could hold, the reactions that had been stalled for minutes raced ahead all at once. The universe began, at last, to build. The first nuclei gathered more particles and climbed toward heavier forms. A proton and neutron paired, and that pair collected another particle and another, combining and rearranging through a short chain of steps. The chain ran swiftly because once the first fragile nucleus could endure, the path upward was open and the particles were plentiful. In a brief and decisive burst, centered near the 3-minute mark, the universe carried out the only episode of element building it would ever manage on its own. The chain led, again and again, toward one particular destination. There is a nucleus made of 2 protons and 2 neutrons that is unusually stable, bound together far more tightly than the fragile first pairing. This is the nucleus of ordinary helium, and because it is so tightly held, it became the natural resting place of the reactions. The building climbed the short ladder and settled there, gathering nearly all of the available material into this one especially stable form. Almost every neutron that still survived was swept up into a helium nucleus. This was, in a sense, the rescue the neutrons had been waiting for. A free neutron, left on its own, would decay within about 10 minutes. But a neutron locked inside a helium nucleus is sheltered, held safely against that decay, able to last, essentially, forever. In the brief burst of building, the surviving neutrons found their refuge, bound into helium, where they remain to this day. This is the moment the universe was 3 minutes old, the moment toward which the whole story has been moving. After the separation of the forces, the sudden stretch, the great cancellation, the forging of the first protons and neutrons, the tipping of the balance, and the long, patient wait at the bottleneck, the universe finally made its first nuclei. For a few minutes, the entire cosmos behaved like the core of a star, fusing light nuclei everywhere at once. But unlike a star, which can burn steadily for ages, this furnace was being pulled apart even as it burned. The same expansion that had cooled the universe enough to permit the building did not stop. It kept right on cooling and thinning the cosmos, spreading the particles farther apart and lowering their energy. Within minutes, the particles were too cool and too scattered to keep reacting. The fire of cosmic building lit, burned briefly, and went out. The whole episode lasted only a few minutes. It is a brief and almost fleeting thing, this single burst of building in which the universe made its first heavier nuclei. It began when the bottleneck opened, near the 3-minute mark, and it was essentially finished not long after, as the cooling and thinning of the universe shut the reactions down. A few minutes of building, and then the long quiet, with the work complete. There is a question that naturally arises here, and it has an elegant answer. Why did the universe stop at helium? Why did it not keep climbing the ladder, building heavier and heavier elements, all the way up to the carbon and oxygen and iron that fill the present cosmos? The universe had the particles and, for a few minutes, the conditions. And yet it made almost nothing beyond helium. The reason lies in a curious gap in the ladder itself. To build elements heavier than helium, the reactions would have needed to bridge past nuclei of certain particular sizes that simply have no stable form. There is no stable nucleus made of 5 particles, and none made of 8. The natural next steps of helium lead immediately to nuclei that fall apart almost as soon as they form. The ladder, in effect, has missing rungs just above helium, and there is no easy way across them. In a star, these gaps are crossed by a rare kind of collision, in which 3 nuclei come together almost at the same instant to leap across the unstable sizes. But such collisions are rare, and they require a furnace that can burn steadily for a very long time, holding its material dense and hot across the ages. The early universe had no such patience. Its furnace was being pulled apart within minutes, with no time for the rare leaps that build heavier elements. So the cosmic furnace closed its books with a short and simple list. It made a great deal of helium, sheltering the surviving neutrons within it. It left behind an enormous quantity of lone protons, the hydrogen that never paired off, and it made only the faintest traces of a few other light nuclei. Everything heavier, every atom of carbon and oxygen and iron and gold that would ever exist had to wait for the stars, still hundreds of millions of years from being born. The short chain that built the helium ran through a few quick steps, each one feeding the next. The first pairing of a proton and neutron gathered another particle to become a slightly heavier nucleus, and these in turn combined and rearranged, trading particles among themselves until they reached the stable form of ordinary helium. The steps happened in close sequence, one flowing into another, so that once the fragile first rung could hold, the climb to helium followed almost immediately. The reactions ran quickly because the conditions, for those few minutes, were ideal for them. The particles were dense enough to meet often, and energetic enough to combine when they met, and at last cool enough that what they built could endure. It was a brief and narrow window in which all three conditions held together. The universe had been too hot for building before, and would soon be too cool and too thin. But for these few minutes, it was just right. Ordinary helium became the natural endpoint because it is bound so tightly. Among the light nuclei, it sits in a kind of well of stability, harder to break apart than the steps that lead to it. Once the reactions reached helium, they tended to stay there, gathering more and more of the available material into that one especially stable form. The building climbed to helium and settled as water settles into the lowest hollow it can find. The contrast with how stars build heavier elements is worth holding, because it shows why the universe stopped where it did. In the core of a star, the gap above helium is crossed by a rare event in which three helium nuclei come together almost at once, leaping past the unstable sizes to form carbon. But this requires a furnace dense and hot and steady for a very long time. The early universe, thinning by the minute, offered no such steadiness, and so the leap was never made. Beyond helium, the universe managed only the faintest traces. A small remnant of the fragile first nucleus survived, along with a little of a lighter form of helium and a vanishingly small amount of lithium, the heaviest the early universe reached in any measurable quantity. And there it stopped. The brief fire had time to make the simplest things in abundance, and the next simplest in whispers, and nothing more, before the cooling shut it down. It is worth pausing on the strangeness of a furnace the size of the whole universe. The fusion that built the first helium did not happen in any one place. It happened everywhere at once, in every region of space, because every region was equally hot and equally dense. There was no special site of creation, no central fire. The making of the first nuclei was spread evenly through all of the cosmos, the same event unfolding in every direction without a center. And because it happened everywhere, its product is everywhere still. The helium made in those minutes was not gathered in one spot to be carried outward later. It was already spread through the whole universe at the moment of its making, a uniform seasoning of the cosmos. This is part of why the same quarter of helium turns up wherever the oldest matter is found, in every direction across the sky. It was made in all places at once, and it has been in all places ever since. There is a gentle wonder in that evenness. The first creation of the elements was not a local event with a particular home, but a quiet thing that touched every part of space alike. Wherever there is ancient matter, it carries the mark of those 3 minutes, because those 3 minutes happened there too. The beginning was not somewhere else. It was everywhere, including the very place where each atom of the present now rests. The first 3 minutes, in other words, set the table with only the 2 simplest ingredients. The rest of the long list of elements is a much later gift, forged in the cores of stars and scattered by their deaths across the ages. But the foundation, the hydrogen, and the helium, from which all of it would later be built, was laid in those first minutes. We turn now to that foundation itself, the recipe of the cosmos as it stood when the brief fire went out. When the brief burst of building ended, the universe had a definite composition, a recipe of simple ingredients settled into place. And what is remarkable is how close that recipe is to what we still measure today in the oldest and least altered material in the cosmos. The universe came out of its first minutes as roughly 3/4 hydrogen and 1/4 helium by weight, with everything else amounting to little more than a trace. The hydrogen was the most abundant by far. It was simply the lone protons, the ones that never found a neutron to pair with, never climbed the ladder, never became anything heavier. They remained as they were made, single protons, and they made up about 3/4 of all ordinary matter by weight. The most common substance in the universe is also the simplest, a single particle left over from the first minutes, unchanged ever since. The helium made up about 1/4 of the ordinary matter by weight. It was the stable nucleus, into which nearly all the surviving neutrons had been locked. 2 protons and 2 neutrons bound tightly together. Its exact proportion was set by the balance of neutrons to protons that had frozen in earlier, near 1 neutron for every 7 protons by the time the building began. From that balance, the amount of helium follows directly, 1/4 of everything by weight. It is worth pausing on how the recipe traces back through the whole story. The amount of helium depends on how many neutrons survived to be built into it. The number of surviving neutrons depends on the freeze-out ratio and the slow decay during the wait. The freeze-out ratio depends on the slight weight difference between the neutron and the proton, and on the rate the universe cooled. The composition of all matter rests on a chain of small quantities, each one set in the first minutes. Beyond the hydrogen and helium, the universe made only whispers of anything else. There remained a small trace of the fragile first nucleus, the proton-neutron pairing, most of which had been consumed into helium, but a little of which survived. There was a trace of a lighter form of helium, and a vanishingly small quantity of lithium, the heaviest nucleus the early universe managed to make in any measurable amount. Beyond that, essentially nothing. That small surviving trace of the first nucleus turns out to be quietly important because it is a sensitive gauge of the early universe. The fragile pairing is so easily destroyed that the amount left behind reveals how dense the universe was when the building happened. A denser universe would have consumed more of it into helium, leaving less behind. The small remnant that survives, measured today, tells us how tightly packed the cosmos was in its first minutes. This recipe is not a minor detail. It is one of the strongest pieces of evidence that the whole picture of the first 3 minutes is correct. The proportions, worked out from the physics of those minutes, match the observed amounts of the oldest material in the universe with remarkable accuracy. When the prediction and the measurement agree so closely across something as basic as the composition of all matter, it is a sign that the understanding is sound. The helium is especially telling. The amount of helium in the most ancient gas, about 1/4 by weight, is very hard to explain by any later process. Stars, on the whole, build heavier elements out of hydrogen, and they do not produce this universal flaw of helium found everywhere we look. That uniform 1/4, the same in the oldest material across the entire sky, is the signature of a single early event shared by all of it, the building of the first 3 minutes. There is something quietly moving in considering how close all of this is to hand. The next time there is a glass of water nearby, the hydrogen within it is almost certainly original. Those single protons were forged in the first minutes of the universe and have never since been changed. Some of the oldest things in all of creation are also among the most ordinary and the closest, present in every drop of rain and every river and every breathing body. The same is true of the helium that drifts in the air and rises in a balloon. A portion of it traces directly back to those first 3 minutes, made in the brief cosmic fire and carried down through more than 13 billion years. The beginning of the universe is not only ancient history, sealed away beyond reach. It is woven into the most common substances around us, present in the water and the air, as close as the next breath. So, the recipe of the cosmos was set: 3/4 hydrogen and 1/4 helium, with the faintest traces of a few light nuclei and nothing heavier. This was the foundation from which everything later would be built. The first stars would gather this simple material and begin, slowly, to forge it into the richer list of elements. But the foundation itself, the simple starting stock, was laid in the first minutes and never replaced. It is possible to see, in simple terms, why the helium came out near 1/4 by weight. By the time the building began, there was roughly 1 neutron for every 7 protons. Each helium nucleus takes 2 neutrons and 2 protons, so a pair of neutrons draws in 2 protons to make 1 helium, leaving the rest of the protons as lone hydrogen. Working through that simple counting gives a universe about 3/4 hydrogen and 1/4 helium by weight, which is just what the most ancient matter shows. The small surviving trace of the fragile first nucleus serves as a kind of measuring instrument for the early universe. Because that nucleus is so easily destroyed, the amount that escapes into the present depends sharply on how densely the early universe was packed. A more crowded universe would have consumed almost all of it into helium, leaving very little behind. The trace that remains, carefully measured in ancient gas, reveals how much ordinary matter the universe held, and the answer agrees with what is read from the glow of the sky. Not every prediction matches perfectly, and it is only honest to mention the one that does not. The amount of lithium the early universe should have made, by the same calculations that get the hydrogen and helium right, comes out somewhat higher than the lithium actually found in the oldest stars. This gap is a genuine open question, neither hidden nor resolved. It may point to something not yet understood about those ancient stars, or about the first minutes themselves, and it is studied with real interest rather than embarrassment. The proportions are measured by seeking out the most ancient and least altered material that can be found. Stars build heavier elements and seed them back into space, so any gas that has been through many generations of stars is no longer pristine. But in certain quiet places, in old and little changed clouds, and in the atmospheres of the most ancient stars, the original recipe still shows through, close to how the first minutes left it. It is there that the predictions are tested, and there that they hold. And the recipe remains close at hand, which is part of its quiet wonder. The hydrogen in a glass of water, the helium that lifts a balloon, carry within them a portion that traces straight back to the first minutes, unchanged across more than 13 billion years. The beginning of the universe is not sealed away beyond all reach. It is present in the rain and the air and the body, as near as the next slow breath. It is worth resting on the agreement itself, because it is the quiet triumph of the whole picture. The proportions worked out from the physics of the first minutes, the 3/4 hydrogen and the 1/4 helium, and the faint trace of the fragile first nucleus, are not adjusted to fit what is seen. They follow from the physics alone, and then they are found to match the oldest matter in the sky. When a calculation made from first principles meets the measured world, and the two agree, it is the surest sign that the understanding is sound. With the building finished and the recipe fixed, the dramatic events of the first 3 minutes were complete. But the universe was far from the clear, star-filled cosmos of today. It remained a hot and glowing thing, its ingredients made, but not yet assembled into atoms, its long patience just beginning. We turn now to what came after the third minute, to the long and luminous wait that followed the brief cosmic fire. By the time the universe was a few minutes old, the building was finished, but the cosmos was still nothing like the sky we know. It remained a hot and dense glowing fog, filled with the bare nuclei that had just been made, with free-roaming electrons, and with an intense sea of light. The electrons were not yet attached to the nuclei. They were still too energetic to be captured and held, and so whole atoms could not yet exist. In this state, the universe was opaque. Light could not travel freely across it, because it was constantly scattered by the swarm of free electrons, bouncing in every direction the way sunlight is scattered inside a thick fog. There was no clear line of sight anywhere. If one could somehow have looked out across the universe then, there would have been nothing to see but a uniform glow in every direction, a cosmos filled edge to edge with light that could not get anywhere. And so began the long wait. The dramatic events of the first 3 minutes were over. The forces had separated, the universe had stretched, the great cancellation had left its residue, the first nuclei had been forged. But the cosmos was far from finished. It would expand and cool for a great span of time, hundreds of thousands of years, before the next great threshold arrived, the moment it cooled enough for electrons to settle onto nuclei and form the first complete atoms. That later moment, when the first whole atoms formed, was when the fog finally lifted. As the electrons settled onto the nuclei, the universe cleared, and light could at last travel freely across it for the first time. The cosmos became transparent, and the light that was set free in that moment still travels today, cooled and stretched into the faint glow that fills the sky. But that clearing is a story for another night. Here, the tour ends with the universe still glowing, its ingredients made, its long patience just begun. It is worth asking, before we close, how anyone can claim to know any of this. No eye and no instrument was there to witness the first 3 minutes. The universe was opaque then, and remained so for a long time after, so there is no direct image of those minutes to be had, and there never will be. And yet the account is not guesswork. The early universe left fossils, and they can still be read today. The first fossil is that faint glow that fills the entire sky, the light set free when the fog finally lifted. It has cooled across the ages from a blinding fire to a whisper barely above the coldest temperature there is. Its presence, its exact temperature, and the faint pattern of slightly warmer and slightly cooler patches woven through it all match what the early universe should have produced. Those patches, in particular, are the grown forms of the tiny ripples planted in the sudden early stretch. The second fossil is the recipe itself. The proportions of hydrogen, helium, and the trace light elements can be measured in the most ancient and least altered gas in the cosmos, material that has been little touched since the beginning. The measured amounts line up closely with what the physics of the first minutes predicts. The small surviving trace of the fragile first nucleus is an especially precise gauge, revealing how dense the early universe was, in agreement with what is read from the faint glow. There is a quiet strength in the way these two fossils agree. The faint warmth of the sky and the proportions of the simplest elements are two separate records of the same first minutes, written in entirely different forms, and they tell the same story. When two such different records point to the same conclusion, the confidence does not rest on any single measurement. It rests on convergence, on independent paths arriving at the same place. There is even a third fossil, fainter still, and beyond our direct reach, the relic sea of neutrinos set free in the first second. It has not been caught directly, because the neutrinos interact too weakly to be easily sensed. But its weight and its influence are written quietly into the other records, exactly where the story says they should be. The first 3 minutes, then, are not a tale told in the dark. They are reconstructed from real and present evidence. It is worth resting, at the end, on the strangeness of the proportions of it all. The universe is well over 13 billion years old, and in all that long sweep of time, the events that fixed the basic composition of ordinary matter were essentially complete within 3 minutes. Almost everything that has happened since, the first stars, the galaxies, the worlds, the slow emergence of life, has been built from a stock of hydrogen and helium that was settled in those opening moments and has barely changed in proportion. Everything that came later is, in a sense, a slow elaboration of that brief beginning. Stars gather the first hydrogen and fuse it, building heavier elements one generation at a time and scattering them to gather again into new stars and worlds. But the raw material, the simple foundation, was laid in the first 3 minutes and never replaced. The cosmos has spent more than 13 billion years rearranging what it made in its first 180 seconds. It is a strange comfort to realize that the opaque early universe was not empty or dark, but full of light that simply could not travel. The cosmos was luminous from edge to edge, glowing softly in every direction, and that glow was not lost when the fog lifted. It was set free to journey across the ages until it reaches us now as the faintest whisper of warmth in the sky. The light of the early universe never went out. It only waited to be released. The moment the fog finally lifted, long after the first minutes, deserves a gentle word before we close, because it is the next chapter of the same story. When the universe had cooled enough for the electrons to settle onto the nuclei and form the first whole atoms, the light was set free, and it has been traveling ever since. That released light is the faint glow we now find across the entire sky, the oldest light there is, the first clear image the universe ever offered. That glow is also a kind of wall, the farthest thing any telescope can ever see by light. Beyond it, toward the first minutes, the universe was opaque, and no light can carry an image across that fog. So the glow marks the edge of the visible past, the surface beyond which the early universe keeps its own counsel. Everything before it, including the first 3 minutes, must be read from fossils rather than seen, inferred from the faint marks those minutes pressed into all that followed. It is worth resting on how much the universe remembers of itself. The proportions of the simplest elements, the faint pattern in the glow, the gentle weight of the relic neutrinos, all of these are records of the first minutes, kept across more than 13 billion years. The universe did not forget its beginning. It carried the marks of it forward, woven into the most ordinary matter and the faintest light, where patient observers could one day find them and read the story back. There is something quieting in that idea, that the beginning was never truly lost. The first 3 minutes are gone, unreachable, finished long before any eye existed to watch them. And yet they are not erased. They linger in the hydrogen of every sea, in the helium of every star, in the steady glow that fills the dark between the worlds. The universe keeps its oldest memory in its most common things, close enough to touch. So we have followed the first 3 minutes from the edge of time to the forging of the first nuclei, threshold by threshold, watching a simple beginning unfold into the foundation of everything. The forces parted. The universe stretched. Matter outlasted its mirror by the thinnest margin. The first particles formed, the balance tipped, the long weight held, and the brief fire made the hydrogen and helium from which all later things would be built. And there is a quiet calm to be found in that thought. The universe did its most urgent and decisive work long ago, quietly and completely, and then settled into a patience measured in billions of years. Everything since has been unhurried. The hydrogen forged in those 3 minutes is still here, in the stars, in the rain, in the breath you are taking now. Let that thought settle gently. Let your body grow heavy and your breathing slow. Rest now, knowing the universe finished its first great work long ago and has been unhurried ever since. Sleep well, and good night.